probably Michaelis-Menten enzyme that is the limiting step. So that's why the kinetic model looks just like the Michaelis-Menten model. Okay. And it really works the same. The meaning of all of this is the same as for Michaelis-Menten. So there's nothing really new there. And this actually applies to cell growth. Okay. We can also pay attention to things like substrate inhibition, which I already mentioned. If your bug gets inhibited by the concentration of too much substrate, then you don't want to feed it too much. Simple solution to the problem. So we use a controller for feeding the substrate, which is exactly what we're going to do, and we're going to feed it carefully, and we're going to figure out what the rate should be so that we don't overfeed. Okay. There's also product inhibition, and if you are producing a product, a chemical product, there usually is a value over which you can't maintain cell growth. And it may be due to the actual product, or it may be due to an intermediate in the process of reaching that product that builds up, and then you cook the bugs, or you pickle them. Okay, so then this is going to be the same concept as inhibition by toxic compounds, such as the intermediate in the process. Okay. You learned about maintenance requirements, so basically you can measure maintenance in terms of how much substrate is taken up per bug. Okay. There's also going to be an oxygen maintenance. We can also talk about product formation. This is the specific, there's that word specific again. Okay, so it's the product, the rate of product formation, dP over dt, normalized to the concentration of bugs. Okay, so that's QP. And the QP is going to be, it may have a component that is growth associated, and it may have a component that is not growth associated. Okay? Sometimes bugs can produce a product even when they're not growing. They're basically just functioning as an enzyme, or a series of enzymes. They don't need to be growing to maintain that process. In that case, it would have a B. It would just be the beta. The alpha is when you have to have the bugs growing or growing slowly to get any product formation. And so the beta is relevant for secondary metabolite products such as antibiotics, and the alpha is relevant for primary metabolite products such as ethanol and 1,4-methyl. It's optimal if you can somehow decouple growth from your product formation. If you can get rid of this whole term, and then you don't need to have a lot of bugs present in the process. You don't waste a lot of carbon producing bug, but you can just get enough bugs and then you produce as much product as you want. That's the optimal process. Okay, so our process is going to be fed batch. Starts out the same as a batch process. Put the media in, put the bugs in, it grows. We're just controlling the pH and the temperature and the oxygen, and then when the substrate is all gone, then we start feeding. And that's why it's called fed batch. So the only thing we're going to add is some substrate into the process, and we're going to feed that until the tank fills up. So that's going to be what we're going to do. So these are the different options for feeding, and we are going to do the linear feed. It could be a ramp, okay, which means that you could steadily increase the rate of the feed, okay, or it could just be a constant value. So you turn on the pump feeds constantly. There's no change in rate of feeding. Okay, if there was a change in the rate of feeding, it could have it could be an exponential feed. That's actually kind of interesting because cells grow exponentially. So you're basically going to give them everything they want, just at an exponential rate. So that works. There's also pulse feeding. Pulse feeding, I'm not sure that there's any real advantage to this. It's generally done when you don't when you have to monitor it with an operator. Okay. And then there's the same kind of concept as on demand. We talked about that in our control. Okay. So these are the basic operating equations for a fed batch bioreactor. I think you've seen these. But the concentration of cells at any time is equal to the initial concentration of cells plus the yield coefficient, yield of bug on substrate, times the amount of substrate you started with minus the current concentration. Okay. So the concentration of substrate in the bioreactor. So when the substrate runs low, then you begin feeding, and the volume of the reactor begins to increase. The volume of the reactor increases according to V0, which for us is 2 liters, plus the flow rate times time. Okay, so we got all that. Right, so that's a fed batch bioreactor. And the concentration of cells in our fed batch bioreactor is going to be at any time x0, what you started with, plus the feed rate times the deal of cells on the substrate times the concentration of substrate in your feed solution times the time change. Okay. And so